I'll take a moment to introduce Dr. Abhishek Chopra as the next speaker today. Dr. Abhishek Chopra is the founder and CEO of BQP, and they lead a very amazing organization. It's a young startup, but they're already doing a ton of different things. I would encourage everyone right now to just take a moment, Google BQP, and learn about their organization. But otherwise, you are in very good hands with Dr. Abhishek.
Thank you, Vardan. And this is great. The program that you guys have put together, I'm really excited to be here. So thank you so much for inviting me here today. Good morning, good afternoon, good evening to everyone. Myself, Abhishek Chopra. I'm the founder, CEO, and Chief Scientific Officer at BQP. Just a quick background and why what we're doing here makes sense. I'm an aerospace engineer and a computational scientist by trade. Develop large-scale simulation codes, particularly in computational fluid dynamics. And that has been a term that has stayed true throughout my entire life, I would say. I started from Rutgers, which is where my bachelor was, went to RPI, not so far from Bryan here and Naval Nuclear, where I got my graduate work going, where as I mentioned, I was developing these large-scale CFD codes. One of the simulation that you see on the bottom right is understanding the flow around the tail of an aircraft. Now, that simulation itself, performed by my colleagues and in the lab, it has actually taken 6 months on 250,000 computers running parallelly. So when I saw this and did this kind of simulation, my other work, which you see on the top, is understanding this. This is the computational fluid dynamics of electric VTOLs. So you have two rotors in front and back. How does the front rotor affects the back rotor? So these are the complicated engineering problems we tend to answer with tools like this. So you can understand how critical a tool like computational fluid dynamics and in general engineering simulation is. But the challenge with these tools is it's computationally very expensive. It takes a lot of time, as I mentioned in my anecdote. So one of the things that I have been trying to do is basically how to accelerate and make these simulations more realistic, but at the same time more cost efficient and possible. So my first attempt to do that was with Oak Ridge National Lab and NVIDIA, where I was basically bringing these codes from CPUs to GPUs. Got the opportunity to run on one of the largest supercomputers of the world back then. And what we found out was that even though we successfully ported the code, we were getting suboptimal performance improvement. And the reason for that is because um, the algorithm that go behind these tools are just outdated and haven't changed in past 40 years. So BQP essentially became my second attempt to solve the problem, where I'm working with my best buddy from undergrad at Rutgers, who's my co-founder and CTO of BQP, and my second co-founder, who's from computational finance background, who has appreciation of these kind of simulation, but also from finance side, which is exactly the theme of this whole thing that the organization here has put together. Primarily because of the fact that partial differential equations are almost everywhere. So yes, I'm going to talk a lot more on CFD, but the implications of this is in many other fields. So just quick word about BQP. We are a dual use startup based out of upstate New York in Syracuse. And what we're doing is accelerating modeling and simulation with quantum algorithms. Today, we are doing that on existing CPUs and GPUs, but at the same time, we're getting ready for the day when quantum computers become industrial scale. So that's the R&D part that I take care of with my role of the Chief Scientific Officer. To do this, we have raised about 6.2 million from venture capital, from 600K from government grants. The beachhead market for us is aerospace and defense. So that's what you see our design partners at the bottom. There are several large organizations that we are currently working who are seeing the value with our quantum inspired approaches, especially in optimization. But at the same time, as I mentioned, what I'm going to talk about and highlight today is going to be on other areas of R&D, which are equally or more important in this area. We were the winners of the Griffiths Institute in Rome, New York, on the Hustle Defense Accelerator, and also the winners of the Quantum World Congress National Security Startup Competition. So with that being said, let's dive into where the challenges with engineering simulations lie and what are the things we can be doing. So here I'm highlighting a workflow from the start of the process, design process, to the final decision process. So how you start with that is you define, what you're trying to do the simulation for. Then you have physics-based model. So that's where the FE and CFD comes in. This is the box I'm going to talk the most about. So let me bring the pointer as well. So I'm talking about this part right now. And this is where most of our focus from this challenge point of view will be. But this is just one part of the entire design process. Then you have so-called design experiments. So imagine if you have a vehicle, let's take aircraft. Aircraft has many components, and each component has to go through multiple design simulations. So you test different conditions, and that's what the design of experiment basically comes in. So you have to test each with a CFD. So at times in industry, you have 10,000 design simulation to be performed for each component. Hence, if one simulation is taking 6 months, you can do the math. The 6 months into 10,000, that it's just impossible to do that kind of a thing. So industry currently has to sacrifice that. They perform very limited number of simulations for those things. So that's what we want to eventually solve for when we're doing this. But let's say you get the ability to do so, then you have the design of experiments where you basically create an entire design space. Then you have something which is called surrogate modeling. And that's where you have an approach called physics-informed neural network. So you're bringing AI with simulations there, PDEs there. So that's one of the other areas that we're working on. And also next to that is inverse design. I'll not talk too much about it, but if somebody's interested, happy to talk more, or you can see our papers on that. And then comes the optimization part. This is another area which is what we are doing today, which is called an inspired approach. And that's where we are using evolutionary approach. So let's say we move forward with that. The last part of the process is uncertainty quantification. That's where we have been working on the area of quantum Monte Carlo. So that you can see that just in engineering simulation, different algorithms within the quantum realm can fit into this entire design cycle. So now going a little bit deeper into our approaches and the timelines that we are thinking, again, what you see on the bottom, the timeline, number of years is purely from a algorithmic point of view. I'm not talking about that the hardware point here. So as a software, as an algorithm company, that's what we focus on. On the top, you will see different paradigms, which I think most of you are aware about. So how we are thinking about is in near-term optimization, where we have quantum-inspired optimization. There's some work on quantum native optimization that has already begun with us. And then we have the data-driven approaches where we are doing quantum assisted physics-informed neural network. And then you have the long-term approaches, which is where we will concentrate a lot on the third piece, which is the hybrid quantum classical finite method for CFD. And then the last part is quantum Monte Carlo, which is what we're doing. So now, just to give a relevance of why these are computationally heavy challenges. So here is an introduction, a very quick primer on computational fluid dynamics. What we talk about here is two partial differential equations. We have the continuity equation on the top, and then you have the momentum equation at the bottom together, which makes up the Navier-Stokes equations, right? Now, the challenging part is that you have a second order, and in this second equation, which is a computationally heavy part, it's second order, and then also has non-linearity into it. So how does this affect? Is basically you want to model like these fluid motions are describing phenomena which are very small scale to very large scale, and what can be resolved. So of course the large scale is much more easier to resolve. That's where what the state of the art today is, I would say, is RANs in industry. So RAN simulations where you're doing everything, you're modeling. So you're not actually solving the equation, you're modeling the equation in RANs, and especially this term that I'm highlighting here. Now, what I worked on as part of my graduate work is large eddy simulation, where you are resolving. So you're actually solving a lot of these eddies, but very fine scales, you're modeling it, because that's where the computational model comes from. And then the goal which we want to all reach towards is this direct numerical simulation, which is basically you are solving everything and not modeling anything. And when you do start, when you start doing that, you get very high accurate simulation. Accuracy becomes a very important thing, but computationally, it's very, very expensive to do so. To give you guys a sense of how this works, this was a work performed by Stanford Center of Turbulence Research in 2012 on supersonic jets. The grid sizes is a function of how much can you resolve. The finer your grids is, the finer you can solve. The coarser your grids is, the larger you can only solve. Right. So here the grid size to resolve this sort of supersonic jet simulation, let me see if I can showcase this simulation at the same time, was 137 million. So you're solving those equations that I showed in previous slide in all these 137 million boxes. Now to do so, it requires 1.5 million cores. At that time, it was one of the largest studies and the largest use of high performance computers that we saw. What you see in this diagram, all this is basically fluid flow. So you can see things which are very complex, very chaotic. It's almost impossible to understand it, but it's also even critically important to understand these, and hence we use tools like computational fluid dynamics. Next study, which something that we have been benchmarking against, is this 2023 work, which was the Gordon Bell Award nominee, did a turbo machinery flow. So the propulsion system inside your aircraft, your jet engines, basically, very hard to resolve. We are just considering few of its component, not even an entire jet aircraft. So the turbo machinery flow here, 1.69 billion mesh. So you can see almost an order of magnitude increase in 10 years we got in grid sizes. But the high performance computing core that it required was 19.2 million cores. Very, very expensive simulation, almost impossible for industry to perform that at large scale. And the last is, which is the goal, that the vision that we started this company with, which was direct numerical simulation of full aircraft. So as I showed in my previous slide, that's the goal eventually, but the grid requirement is 10 to power 16, and it's almost impossible until the year of 2080 to resolve that with high performance computers. So this becomes the entry point of why we need to add quantum computers into our data centers, and how will we use it for a problem like computational fluid dynamics of full aircraft. Now, you may ask, why is this important? And I can only point to very quickly an unfortunate incident that happened a few days back, and knowing in India with the Air India flight. So things of that could very well be avoided if we do our engineering well, if we know and do things in the right way. So this is why it becomes very, very critical. But again, as I mentioned, we are limited by our compute bottleneck. So essentially, more computing power is required. One of the ways we can do is how we're doing today, which is brute force method, making the systems larger and larger. But by making the systems even larger, the bottleneck comes from how do you supply energy to that? Where does the real estate come from? We are already seeing that with the advent of AI and generative AI, that we are talking about energy cost and energy efficiency that's high off the roof. Another way which people have been trying, but this also will not scale anymore, and this is where the engineering way of saying that quantum is needed, is making your transistor smaller and smaller. You've got to a point where you've got to atomic scales where laws of physics starts to apply any which way. So that's an entry point of why we need to look at the next technology, which is the quantum in this case, which is why we are all here. Even from the computational fluid perspective, this chart was put by NASA and the top scientists in the world of how this world of computational fluid dynamics will evolve. This was laid out in 2014 first time. So they put this 15-year sort of roadmap in there. And you will see a very key word here, which is CFD on revolutionary system, where quantum was first mentioned without even people knowing that that could even be possible. And it was really it was 2020 and 2025, which is exactly the timeline BQP has been working on, and then eventually a goal of 2030 vision. So this is now prepped up everybody for why CFD, why performance, why competition is a bottleneck, and why we need to look towards quantum. One thing before I go forward is we believe in the world in future, at least in BQP, we believe in the world of future data center being CPU, GPU, and quantum computer, or QPU, you can say. It's not going to be entirely quantum. That's not the world we believe in. And hence, it's so critical that when you take such problems, how do you break down the problem? Which part of, let's say, CFD or partial differential equation will go on to CPU, which will go on to GPU, which will go on to QPU, is a vectorization problem to be solved in future. So that's what essentially we are working towards. Now, in the literature, this is a very recent phenomenon. Like over past 5 to 6 years, we've seen a lot of work starting to happen on this, but everybody hinting that we need bigger and bigger systems, we need better algorithms. So that's where we were motivated to be part of this this workshop and the challenge areas that we're going to do over the next few months. But just to highlight, there are different parts of partial differential equation solving which you can target. The top three are primarily ones you will be affecting the linear system of equation, which is the critical part. So you have a partial differential equation, you solve it, you bring it to an ordinary differential equation, you solve it further, you bring it to a linear system of equation. So those are the three areas. So the first three primarily targets the area of linear system of equation. And what we have been working at BQP is number one, which I'll highlight a little bit more. The fourth is which affects um, is more towards the quantum side of things, meaning it's more quantum prone, it's more closer to the quantum thought process. But we are seeing a lot of interest in the area of quantum lattice Boltzmann equation. We have not looked too much into that area, primarily because of the fact that lattice Boltzmann method, which exists in the classical CFD, is useful for very certain problem sets. For the kind of problem sets we are motivated, which is the more broader and more large scale and high fidelity CFDs required, such as the one I showed in the NASA CFD 2030 vision, lattice Boltzmann plays not a lot of role in that roadmap. So hence we have not invested in that. But there are many players, and the reason they have been interested is because it's closer to quantum, so they're more quantum prone. And the last, which we are very motivated and we are very interested, which is also what we'll put up as a challenge, is the hydrodynamic Schrodinger equation, which is like you don't start from the Navier-Stokes equation and try to solve it with quantum. It's like a completely opposite way of thinking, which is what I will highlight in my next slide. Whereas hydrodynamic Schrodinger equation is you start from the quantum lens at the step zero, and then from there you go solving. So every challenges that come with scaling these kind of approaches come in would be avoided in hydrodynamic Schrodinger equation. As I mentioned, that's one of the areas will be looking at, and the other area we'll be looking in as part of this challenge is the quantum tensor network. But before we go there, I just want to highlight the work that we have been doing in this, which is the approach number one. So our goal here is targeting the linear system, which is where the computational bottleneck really lies in classical CFD, and that we're doing with variational quantum linear solver. So if you see how does the partial differential equation sort of is being solved today, is you have the discretization, so you can choose finite difference, finite element, finite volume method. You discretize it, and then with certain manipulation and in the implicit and semi-implicit schemes, you end up with a linear system of equation. And this is the part where we are basically solving with variational quantum linear solver. We started from the Bravos implementation, but over the years we have evolved because this was laid out for essentially solving linear system. But the kind of linear system we start getting in computational fluid dynamics and other parts of engineering simulation is very, very challenging, and you need more innovations. We have a upcoming paper at AIAA conference on those scalability challenges, which I'll not talk too much about here today, but I'll show the more work, the fundamental work we did, which we published last year, and then the post-processing steps that come into the picture. So here, when we are targeting the equation that we basically took is 2D Berger equation, which is a simplified form of the Navier-Stokes equation that you folks saw earlier. Which to say we are taking the complex part of those Navier-Stokes equation, but not the entire equation. It's called 2D Berger equation, where we have the transient and the nonlinear partial differential equation. The discretization method we chose was a finite difference method, and the benchmark was done against the state-of-the-art linear solver, which is the GMRES. So here are the contour plot for the y velocity for this problem that we set up, and the difference, which is basically the difference between the classical and the quantum method of a linear system. And the good part is in the middle plot, you see the error rate is at 10 to the power minus 5. Now, this was performed on noiseless simulators. We use Qiskit for this thing. And later on, I'll show some results which we have done quantum hardware on. But the system sizes, which was the key thing, because the kind of system sizes, as I mentioned, if you remember from previous slide, we are trying to reach is 10 to the power 16. But you start somewhere first. So we have been starting the scalability from 4 qubits. We have done in this part 11 qubits, and we were able to showcase that this actually works with high accuracy. The further steps, of course, we are doing is scaling this further, testing it on noise-based simulators, and then eventually quantum hardware. Now, one of the things that we have realized that when you start going um, beyond this 11 qubit, and why we want to go there is because we want to increase the complexity of this equation. From 2D Berger equation, we want to go towards 2D Navier-Stokes equation, and we have faced some very challenging scalability issues there. Um, like few of them are related with quantum circuit size, and the other one we have faced is the barren plateau issue that comes in variational circuits, and those we have resolved it. That's the paper that is upcoming in the AIAA conference in few months from now. But this is where we got motivated to look into other approaches here. So just to give you all a sense of how we think about it, where our present work is somewhere here on this range. This graph is basically telling the paradigm on the top, which was similar from what I brought in from earlier, but the kind of problems we want to solve. So today we are thinking of subsonic problems, then we have supersonic problems and hypersonic problem. Hypersonic is the eventual goal. That's also how the NASA 2030 vision is laid out. Now, the challenge going from subsonic to supersonic is you have start getting more complex flow. You have shock waves that start to form. A lot of other things start to come into this. These are the kind of problems we were solving back in our graduate school, myself and my co-founder, who comes from hypersonics background. He was doing his work at University of Minnesota, and the kind of work he was doing was on the realm of hypersonic simulations. So to break the barrier, what we believe in is somewhere around the 20 to 30 logical qubit. Now, this is our current intuition from our resource estimations that we have done, that we believe around 20 logical qubit is where we will start going beyond what classical CFD can do. Now, this is our current understanding. This could move around. It could go to 30, it could go to 15, but this is the realm we are thinking of today. So just to finish this on using this HQCM approach, we have looked into Honeywell simulators run where we have done heat transfer problem on an HVAC plate. We got error of 10 to the power minus 6 on this. Then we ran an actual quantum computer run, which is a frontal impact of a car structural simulation, linear system. We were solving linear partial differential equations, so very more simpler than Navier-Stokes, I would say, where we utilized 27 qubit and the error was 10 to the power minus 3. We have been trying to replicate this work in CFD, but it's very, very challenging to do so. So that's what has motivated us to be part of the challenge, this challenge from Umanium. The two approaches that we are putting forward as part of this challenge is quantum tensor network, and the other is hydrodynamic Schrodinger equation. So a little bit on those quantum tensor network. Why we are investing in that is because first, there's a lot of work on the classical GPU side of things with tensor network that have happened, and the pivot from classical to quantum or hybrid quantum will be easier when we look at quantum tensor network. So that's one of the areas. Its scalability wise is much more the compute the circuits that we might see in these are going to be comparatively less in compared to your HQCFM approach with VQLS. So that's one of the areas we want to invest in. And how we are thinking about this is basically, can we solve a benchmarking problem that we will define as part of the challenge with the quantum tensor network approach? It's not about beating out, it's not about quantum advantage. What it is really about is, number one, what is the resource estimation? What kind of accuracies we are getting? And can we build the map similar to how we have done here with regards to this? Then comes the hydrodynamic Schrodinger equation. A lot of our thought process from the onset has been, we are trying to make quantum work in the classical framework, but to really get the advantage of quantum, we need to think from a quantum lens. So that's where converting the Navier-Stokes equation to so-called hydrodynamic Schrodinger equation through some transformation. We wrote this work back in the day in 2020 when we started it, and when we have been spending time with it, but we have not fully gone into it and investigated. But this seems to be the right forum where we can look at more quantum prone approach here and something which will not meet the challenges of scalability that we are seeing with other method in what we're working. So with that, that's my end of presentation. Happy to answer any question. I hope I'm okay on time and I didn't take too much.
Yes. Perfect. Yeah, thanks a lot, Abhishek. This was beautiful. Okay, we have a lot of questions on this card for you. In the interest of time, maybe I'll shortlist 2 or 3 of them, and then the rest we'll compile and send it to you over email. One question which is really fundamental, and I thought it would be useful for all of them, is understanding what kind of quantum hardware are you gunning for right now? Is it more gate-based? Is it any-link systems in the gate-based approach? Do you have certain qubit modalities which are more relevant towards solving PDEs? What are your thoughts on that?
That's a great question. We have tried as part of one of the challenges that we were participating, which is the BMW Quantum Challenge. That's the time when we tried the annealing approach. And we have not, like, we showed some very interesting results as part of that. We were the finalist in that, but we didn't see ourselves being ready for investing in annealing approaches just because of the kind of scales we want to go towards eventually. It's not about showing and demonstrating today, but the scale that we are targeting. And hence we have invested quite more on the gate-based approaches. Even within the gate-based approaches, it again goes back to that slide which I was showing, that which part of the partial differential equation we're targeting. Because some of those part is nothing has to do with accuracy, has to do with fast response. So something like superconducting would be of interest. In other approaches, accuracy matters more than the time speed up. So you might have an ion trap or a neutral atom, which is much more stable, giving you more performance improvement. In short, we don't know yet the answer of which modality will will succeed for computational fluid dynamics. But I'll say one thing, that um, in my belief, it will be a multimodality system that will give us the outcomes that we're looking for.
Perfect. Perfect. Another question we had was on something you briefly mentioned. You mentioned that the future is for hybrid quantum algorithms, right? We'll be using some part on the variational side, using HPC and different type of high computing clusters combined along with quantum. Can you elaborate a bit more on that? Like, what are the specific steps in that entire PD equation which are more suitable for quantum compared to classical?
That's a great question, and that's a very fundamental question. This is just a highlight. This is applicable only for this area, but this could be very much extrapolated to other paradigms also. So when you solve a partial differential equation, my discretization, my post-processing, I am better off doing it on CPUs and GPUs. I don't need quantum computer for that. And it's a linear system which should go on to the quantum, because that's the computationally heavy part. Now, there's hybrid algorithms, which is not what I'm always saying when I say the future will be hybrid. Your quantum algorithm could be a pure quantum native approach. It could be a hybrid approach. That's okay. But how it fits into the bigger solver lens is where I meant that there's parts of the solver which will go on the CPU. So you can say pre-processing, post-processing, it's CPU, GPU better. Quantum is for the actual engine, the solver engine part, which is the algorithm part. I hope that gives some clarity.
Wonderful. Yes, yes.